record on this computer. All right, so we're recording now. Again, I'll record the lessons prior to, so you can watch the videos, and then during the lecture period, you can log in. I can even record the Zooms with the questions and post those on Canvas as well. They're already posted. This lecture is already posted on Canvas. Your time logs, keep track of them on your own spreadsheet outside of classwork, which everything's going to be outside of class now, I guess, even if you watch the lecture. I wouldn't count the lecture hour, but anyway, if you do, let me know. I'm going to post basically a Google form where you can actually view or send in your time logs. It's after spring break. This is pretty much going to be online class for the rest of the year. So everything's going to be online submissions. You will want to log in after spring break during the lecture period, because we will probably be talking about issues with your boards or whatever your project is. You can always meet at other times and then do Piazza posts as well. All right, so Monday, given that the school is closed, Lab 3 report was due today. I am going to be flexible on your completion for this lab and your lab notebook. Hopefully you get it done before too long next week, but because I would like to get it all graded over spring break. But your project proposals, try to get me something on Monday so I can see it and try to get you some feedback. And then the final one will be due, it was supposed to be due, I believe it is on Wednesday, but by the end of next week, you should kind of know what you want to do, because you need to start ordering parts if you need to order parts, or do a little research. But today we're going to learn a little bit about direct digital synthesis, a little more than what we learned before with linear interpolation. Because we're trying to set ourselves up for Lab 2, which essentially in Lab 2, we're going to build a BRAM with a sine wave in BRAM, 1024 values. And I'm going to show you one of the papers that I gave you, and if you didn't, if you're not in class, you can always go to the website and download the spreadsheet. And you guys can't see it, but everyone online can. There's a spreadsheet there, and which we're going to go over that spreadsheet in class. And then there's a handout, which everyone in class already got that handout. Ultimately, for the lab, though, what we're trying to do is we're going to take, before, we were only taking 10 bits to select our address in DRAM, right? So we had a counter that selected the address to read those values, which is fine if you want to generate one signal at one frequency, right? And we have a audio codec wrapper that currently outputs a 48 kilohertz signal. So one sample per 21 microseconds. So if I output every value in that lookup table for that sine wave, I only get a 48 hertz signal on the output. But we're going to learn how to index into that array and then interpret using the other 6 digits on our 16-bit value to interpolate the between values, essentially. Right? So what we're trying to do is sort of like this example is if we're trying to compute a square root of a value using our microblaze, you could use a library that has a function, if you have a compiler with that library, and calculate that value. But if you're doing it multiple times, then you would have to calculate it. Well, if you didn't have that library, you'd have to calculate it using a square root function. Is not a trivial task to do. One way you could actually calculate a square root is using Heron's method. And on the next page, I talk about that a little bit more, which only gets you close to the right value. Heron's method essentially will take your S value that you're trying to average, and you're going to take, depending on the number of significant figures, you're going to execute this function that many times, which is going to take some guess value that you have, n, x of n, for the square root of it, and divide the original S value by that and add that value and multiply by 1/2 to get our next guess value. And then you're basically going through this process, and this is from the website. It goes through this process 6 times to get pretty close value of this 12, 5, 3, 4, 8, the square root of it, right? It takes a lot of math, a lot of division, a lot of times, right? So you can compute it, but it takes some time, right? Obviously, you could look for a mathematical expression similar to that, and it's still going to lead to a timely computation. You could go through and you could enumerate every possible value of x and its square root, which is then going to take up a lot of values in memory. So you have a lookup table in memory and retrieve the value. Seemingly simple, but it would require tons of space to do. We can reduce that space by eliminating the number of entries, and that the spreadsheet that I gave you actually does that. It eliminates those entries, and then we're going to interpolate the values between it. But this is going to introduce some errors into our system, but we'll work through that. So you're going to go and try to get the closest value in that table, and then you're going to compromise based on space, time, and error, right? We don't want to take too much time for calculations. We don't want to use too much space for those lookup tables, but then we're going to also look at the error that the lookup tables actually introduce. We're going to interpolate those values in our partial lookup tables. So definition of interpolation is a mathematical method for creating missing data. What we're basically going to use is averaging the two values around our expected value to find the one we're trying to create. This average essentially is called linear interpolation. So we're going to draw a straight line between the two values and find a value between them. So say you have a value of 0 and 4, say the square root of that. You're hoping your x is somewhere halfway if you're looking for the value of 2, right? And that's kind of what we're going to assume. So you can assume our first value here is y as f of x, and our second value at 4, f of x plus 4, is our z value. And we're trying to estimate the values for x1, 2, and 3 in between by basically saying 1/4 of the way up between the average, halfway up, and 3/4 of the way up. If we did a baseline function, if we just said, okay, rounded down to the nearest value, it would look like this yellow graph where we just have 0 for the all 0, 1, 2, and 3, and then it jumps up to 4, causing a lot of error, a lot more than just with linear interpolation. So let's use an example, and this is actually on the spreadsheet if you want to take a look at that on your own computers. F of 8, so the square root of 8 is 2.8284, and square root of 12 is 3.4641. Right, so f of 8, I put it down at the bottom and I indexed my x-axis with those values. Now, f of x is now square root of x technically, but I'm just using an example. So, and then f of 12 is at the top. You have the baseline, and then you have the linear interpolated graph in the middle. F of 9 would be right here, and we just take that base address, what f of 8 is, plus 1/4 of the way up this line to the next value. So then we subtract the top value, f of 12 minus f of 8, to eventually get adding that quarter value to the base value. we get 2.987. And that gets us pretty close, right? Same thing for f of 10, except it's 2 of 4. And we have the two values that we're looking at and the difference between them. And f of 11. And we get the values based on base plus 3/4 of that difference, right? Linear interpolation. We're just drawing a straight line between f of 8 and f of 12. So obviously this is going to have error, and we're going to take a look at some of the error. I have actually calculated and graphed it for you. But when you're doing embedded computing, sometimes time is of the essence, just like Daniel found out, right? This function basically is a C code, kind of like pseudocode, that explains how to perform linear interpolation in a basic form, right? X of I, X plus I, where I is between 0 and 4, those two values. We're given that f of x is y, f of x plus 4 is z, and then we're going to be given a value of I between 0 and 4 and returning that f of x plus I. This does the same thing that we just talked about. It's taking this delta value, which is z minus y, the top and the bottom values that we're interpolating between, shifting right by 2, giving us a divide by 4, and then adding that delta, or multiplying the delta times our index value. Index value divided by 4, right? Since our values are 4, we're dividing by a 4. And then adding that to y. And doing this after, doing the divide by 4 after we do the multiplication by delta is probably a good idea to do, just because this value, this difference could be pretty small or even 0. If we divide by 2, it's better to do it later when we actually have delta times I. But we'll look at another example that will actually go through that. So here is a smaller square root table. This shows the actual square root values, and if you look in the spreadsheet, I have the full square root table in the spreadsheet. Where are you? Here we go. If you go to the 4-point square root, notice we have every value of x between 0 and 15 and the exact square root values to roughly 6 decimals positions. And then we're going to calculate the rest of those, which are base, offset, and delta, to calculate the difference. But right now, it's going through and it's graphing all those values, the exact value of the square root, and then it has the base values. On some graphs later, I'll show you the difference between them. But then we also have a 4-point lookup table, where we're just going to, instead of taking 15 values in our lookup table, we're going to have 4 values plus 0, essentially, indexed into that array. So you got 4, element 4, which is 16, our value of 16, and the square root is 4, and obviously square root of 4 is 2, and then the other 2 in between, square root of 12 and 8. So we're going to look at that graph, right? And we've talked about this. Square root of 9 is somewhere between 8 and 12, just like I said, between 8 and 12. And if I wanted to find the square root of 9, it would be about 1/4 of the way between 9 and 12. And we're going to generalize this with an equation, right? Square root of 9 is equal to square root of 8, which is the base, plus 1/4 of the difference, or the delta, of square root of 12 and the square root of 8. So the other bounds of that linear graph, right? So we can generalize this statement with actual numbers. We can get the delta value, the distance value, if we subtract 9 from 8. So this is how far up that line we're going, and then this is the distance on the line, right? We got 4, so 1/4 of the way up that line to get that. we're gonna, typically I would normally divide the class up and you guys could calculate out the 16 square roots of 0 to 15, but I already did that in the spreadsheet, so you can take a look at the spreadsheets. That's all there. Already did that, but these are the exact values. But I'm gonna attempt to save some time. I'll let you just go back to the spreadsheet. So what I broke down in the spreadsheet, and if you take a look at it, I broke this equation down into base, right? So I have the base here in this graph. So from 0 to 3, and the square root of from 0 to 3 will have a base of 0. The base value is 0. For 4 to 7, we're going to have a base of 2. So 4 square root of 4 is 2, so that's the base value, right? That base value is the lower mark on that linear line that we're going to interpolate from. We're going to have an offset value, which is in how far we're incrementing up that line. And it's going to be that offset will be in terms of 4, because we're going to jump by 4 through this. And it'll represent how much we're going to offset above that, onto that interval, onto that line. The delta is going to be that distance between the 2 points. So if you look at the delta between the base 2 and base 0, it's 2. The difference between base 2.828 and 2, it's 0.8282. And then from 0.346 to 2.82, you get 0.63, and then 0.53 for the last. Does that make sense? Taking the upper bounds minus the lower bounds to get that delta. How much distance is covered vertically along that line. All right, so we got to get the horizontal distance here with the offset, and then you get the vertical distance. And those, do I have my video playing? You guys know? All right, here. Let's see if I can show that. So if you look, and you have x values, f of x, whatever that is, we're doing the square root, right? And some value from 0 to 4 along this line, f of 0, and then f of 4 here. So you have change in x. That's going to be what? That's going to basically be your offset.
It's really hard to see, by the way.
Can you see?
All right. What it looks like.
All right. That kind of stinks.
It's pretty compressed.
Well, I can write on the screen then too, I suppose. All right. I do have it in there anyway, so let's just go back and look at that. Stop video. Let's go back. Really, all I'm trying to say is pin on the x value. This is going to be delta x, change in x, right? Which is basically offset. Off. And I'm not going to draw it very well. So we have our delta x. That's going to be our offset. The change in y here. Change in y, what is that going to be? Anybody? We just learned about it.
Delta, right?
Delta. Delta. So we have our change in y is going to be our delta value. And that is here. So that is going to be the difference between square root of 12 and the square root of y. And then we're going to calculate that base plus offset times delta. And that's what we're going to be doing when we're indexing into our lookup table in lab 4. we're going to be calculating that function to interpolate those values. And then the error is basically the absolute value of the differences between linear interpolation and the actual true value. So, and that's what we get for percent error. Notice on the base values, they're all 0. And you can actually see that when you look at the graph for the error. So you have linear interpolation. You can see there's a biggest difference here between 0 and 4, so the smaller values, right? The actual square roots are a little bit bowed. That's the purple. But linear interpolation follows it pretty well up beyond there. So between 0 and 4, at 0 and at 4, it's 0, but then you have quite a bit of error here, but then it just kind of has these little areas of error between those base values. So now we can come up with a better function. This one is a specific one to our square root. Using a 4-bit integer, we're going to approximate our square root, and it's going to linearly interpolate that. And we're going to, right now, it's just a type called fixed. We'll set up a specific type in the next example where it's actually going to go through a specific example. Because right now, they're put in we have a lookup table. We're doing the square root of some int 4. So a 0 to 15, right? Int 4, value of x. And I have a lookup table with these 5 values, or 4 values and 0. Those are the actual values for the square root for 4, 8, 12, and 16. And then we're going to have an index and a base. And basically, we're going to take that index, which is a 4-bit number. So, and here's where we're kind of running into a problem with our index, because if we come in with, say, 9, index of 9, shift it right by 2. Well, I'll show you in a bit, but it's where we get into the offset. But if I have 9 here and I shift it right by 2, what do I get out of that? What's the value now? 9, 1, 0, 0, 1, right? If I shift that right by 2, what do I have now? 1, 0, right? Which just happens to be square root of 8, our base, right? 2, index 2. So we look at that, index 2. We plug that into our base. And then, this is where it kind of gets screwy. I would take 9 and I would mask 3 to look at the lower 2 bits of that, which would give me what? What's the lower 3 bits of 9? 1. Exactly. So I have 1, 0, 0, 1, right? So I'm looking at the 0, 1, and that would be my offset. But if I actually shift that right, then I kind of get rid of my offset before I'm actually using it. So that's where, and I'll show you in the next slide, where you do that after you do the multiplication, because you're kind of shifting away your offset value. But then we're going to take x plus 1, so it's going to take the third value, 3.46, and subtract to find the delta of 2.82, so index 2 and 3. 3 minus 2, give us that delta value, and then offset times delta plus our base value. And that returns our square root, right? This is a specific example with a 4-bit integer, and it's using an 8-bit fixed point with a decimal or binary point at the 6th bit. So it's a Q2.6 number. And I'll show you those right here. They're Q2.6. So if I have these values, square root values, if I multiply by 2 to the 6, remember from last meeting, multiply by 2 to the 6, I move that Q2.6 decimal place over, so it's just one whole number. So I don't have to deal with the decimals, right? So that gives me these numbers, and I can truncate them down, basically lopping off those last bits because they don't matter. at this point. We're just rounding down, right? So we get 256. Since I can't represent 256 with 8 bits, I round that down to 255. That'll introduce a little bit of error, but that's fine. The other one is 221, 181, 128, and then 0. I can then represent those as binary just by plugging in the numbers. It's all ones, all 8 bits. The binary point exists only as the programmer or the programmer. So if I do these conversions, it's still just a regular 8-bit binary number. You know where the binary point is. And then these are the values in hex. Those are the same values you'll see here in this lookup table. You go from 0080B5, DE, and FF. And then I send it through. I take my index, shift it right by 2, index into there, so I get index 2 and 3 for the value of 9, right? And then this time, I'm gonna just, instead of shifting the offset by right by 4, or 2 bits, divide by 4, I do that later. So I basically just moved it down after I do the base plus offset times delta. But basically we're masking those lower 2 bits to see how far we're indexing to the next value. So it's 1 divided by 4, 1/4 of the way. Kind of cool, right? You're gonna learn how to do this in hardware.
So then this wouldn't be on something like the microplays. We would do this in VHDL.
You're gonna do it in VHDL, yep.
Okay. If you wanted to implement some sort of other algorithm, would you be allowed to?
That's a functionality, or actually I think that's bonus functionality if you wanna hook the microplays up to your Lab 4.
Oh, sure, yeah.
So yes, you're gonna use, we'll get to that later, but you're gonna use the slider switches to change your increment value. And then you're gonna use buttons to move it up or down, or whatever. So, but we'll get to that later. Linear interpolation. And then this is just the graph in hexadecimal, 2.6 hex, which is kind of cool. What if you wanted to use something like a 16-bit binary? That spreadsheet also goes through and actually makes this a 8-point lookup table on the other tab that indexes from 0 to 8. So we just have a bigger lookup table. It's still indexing, we're indexing by a larger value, right? So we're going from by 16, 0 to 16 to 32, all the way up to 128 in our values. So we're gonna have a lot more error, but then these are the values that I'm basically converting for you and showing you how to do it. Then you can look at it to see what kind of errors we're gonna get out of it. We'll look at that. So to convert this 16-bit value, or these square root values into a 16-bit value, I just multiply by 2 to the power of 6. And I get these values. And then I truncate them down. And then I show you the upper 10 bits, and I showed them in 2 separate columns because the conversions in, there's actually pretty cool conversions, binary to decimal, and things that spreadsheets allow you to do that allowed me to show you these values. And we'll do that in our example as well. So you got your lower bits, these are the fractional bits, and then these will be the whole bits that we are going to be messing with. And they're really the values before we do the square root, or multiply by the 2 to the power of 6. So you have 4 here, 1, 0, 0 for the upper 10 bits, and then 5, and then some fractional bits. And then we got 6 and some more fractional bits, and then this one's 8, no fractional bits. It's kind of cool how that works, right? This, if you graph those, you're gonna have a lot of error here to 0 to 16 for the linear interpolation, but after that it gets a little better. The scale changed a little bit for this error. Definitely a lot of error here on orders of magnitude higher than the values beyond that. Pretty cool though. So let's go through an example. You have this sheet. You can either do one or two things. You can print out the handout, the blank handout that I gave you that looks like this. What we're going to do is we're going to use a Q4.4 format, and we're going to index through this lookup table. This right here is a 16 value lookup table for a sine function. And you notice it goes from the middle, 127, up to almost 255, and then back down to 0, and then back around middle, right? So this is one sine wave in a small BRAM lookup table. We're going to index into it based on 1.1011. Anybody know what that value is? Anyone want to venture to guess?
Well, it's 1 point something.
1.5
plus 0.125.
Yeah.
So that'd be 0.6. 1.65 or something roughly.
Nope. Close. So if you open up the spreadsheet that I gave you online, it actually gives you a really cool way to do it. And it's actually going to graph those values for you if you want to. So these first base and final values are already calculated on the screen. I'm going to show you how we're indexing through this. All we're doing, we're taking this binary. We start at index 0. At time 0, we start with index 0, this value, right? And then I have a lot more values in the spreadsheet than I do on the sheet on your the handout. But if you go along, you can see what everything is. I actually do the binary to decimal conversions for you, right? I divide this value by 2 to the 4th. So I convert it to the basically the decimal conversion. Since we have a Q4.4 value, we're going to index into this lookup table. Instead of going one by one, we're going to index by 1.6875. So we're going to index, and we're going to go over time through 15 clock cycles to see what value actually gets calculated for the base plus offset times the delta. So first one, you got decimal index of 0. The truncated index is still 0. So that value is what is in index 0, which is 127. You can see the cells are actually mapped to that. For the next value, next two values, I'm taking index plus 1. So this 175 minus 127, which these values are here. I actually index into them. And then calculate that delta value. So it's going to subtract them from the left to the right. So the higher one right now, it's the higher one minus the right one, minus the current index. We will get negative indices or deltas off these. Then I do a simple conversion. I show you how I convert those. So 175 minus 127, we get 42. That 42 gets converted to binary. And then we have our offset value. Right now, we're at 0. So there is no offset value in there. That would be the fractional portion. Which the next one for 1.687 actually has an offset of 0.687. And I won't bother showing, I mean, these are just going to go from 1. So you have the value of 2 and 1. We're going to get an offset of 41. Yeah, 216 minus 175. And then calculate our binary for our offset. For this one, it has an actual binary value for the offset. Add the delta, or multiply the delta times the offset. For this first one, it's just 0 times 48. We get 0. For the second value at time 1, we get 41 times 0.0687. So we can actually index up linearly up that line to get 28.1875, and that's going to get added to our base value. So we multiply that. This is just the binary of it. We're going to have base plus that offset. So I get 175 for my base, and then I'm going to add in my offset. And that's going to give me roughly 203. That 203 value is basically 175 plus 28. And then we have our final values of 127 and 203. Notice these are already being graphed down below. See, when I delete that final blue value, it goes away. So as we add these values in, they're going to add them to this chart. So we have our blue line, which is our base plus offset, the closer linear interpolated, and then we have our base address. So first thing let's do, let's go ahead and index into our array. You can actually do what I had done, and it just copies that index, multiplies by 27, which is the 27 is this index value multiplied by 2 to the power of 4. So you don't have a fractional value. So you can take that, copy it if you want, and you can just paste them in, paste the function, and you add on those values. But then you get a problem when you hit to this value, which just happens to be what? Let's do the
points. 125.
I'm going to go ahead and convert this.
That's 125. 125 plus something else would be like 15.75. No, 15.0175.
Well, it's 10. This one's 10 times 27. So this should be 270. And an 8-bit number, what's the largest value you can have? So if I'm in a 8-bit value,
the largest value.
255, right?
Yeah.
So I can't represent an 8-bit value. That's why it's giving me an error. So I just need to subtract 256 out of there to get those to work. So it's going to roll over, right? When we have a counter, if it's a 8-bit counter, we're going to roll over. So we're going to add. So if I take, I mean, you can actually look on a calculator. That's kind of the nice way to look at it. So if I have decimal 27 plus 27, we're going to get rid of the fractional portions, right? As I get up there, 243, this is the step before it rolls over, right? And I go to 270, notice I get that value. Basically, what is that? 14? 14? Instead of 270, because this bit goes away. It basically is a carry out, right? So that's what's going to happen for the last ones. You're going to just keep going and continuing on and rolling those values over. And I can plug those in. So I already did the conversion back to the decimal values. So we're adding that 1.6875. And this shows the fractional value instead of the actual decimal value. So these are the indexes into our array. We're going to start at 0. We're going to go to 1.6, which is somewhere between these two. And then the next value is here between 3 and 4. And then we have a value of 5 between 5 and 6. And then a value between 7 and then 8 and 9, and so on and so forth. And we're interpolating those values between them, essentially. Truncating it down, we just get rid of everything past the decimal point, which you can copy that function. And that's fine. I have this. 26. Kind trying to make it easier for myself. I copy these values. That's the truncated values, 1, 3, 5, 6, and so on and so forth. And then you can index into your array. So we're going to try to get the value of 3. So that's going to be what? 244. You can type in the value for 3 there. This one is a value of 5. So I'm just going to say equals that value, 244. Notice they're the same value, right? This value is going to be index 6. That's our base. This is index 8. Click on that. Equals index 10. Equals index 11. That's going to be 9. 13. Equals 15 equals 0. We're going back around. 2. Value of 4. 5. And last one is index 7. Right, so we have our base addresses, and notice we have a base address graph. Doesn't really look like it's pretty janky, right? So we have a lot of error on there. Our sine wave does not look very good, right? We have some little dog legs coming out, and yeah, it's pretty gruesome. It's gonna sound horrible too. So now we need to find our delta values, so we're gonna just take those upper and lower values. I'm gonna kind of cheat this one, just to save some time, and copy those values. Basically, I'm looking for the next value in the index. So if it's index 3, I'm going to look for 4 minus 3, plug those in there. So I get 153 or 253 minus 44, and then I can copy the subtraction. Copy those values in, and we're going to find our delta values. Notice some of them have a negative value. That is fine. We're going to have that, right? You're going to have the next value being lower than the base value. So our deltas will be negative sometimes. So we got that. And I just copy in the delta values just to make it easier. So actually I already have that. The binary delta, I actually have a function that'll calculate that for you too if you want. This is pretty handy.
And so it does do proper decimal then, like the fixed point decimal type?
Yeah, you can fix it to a certain value, for a certain number of bits. So you just have to select the number you want to convert. Whoops, I want this one. All right, and it converts this to 8 bits. So if I take that formula, copy it, and then paste the formula down. Notice, although any one that's negative, it adds an extra couple ones in the front of it. So you just have to be aware of that.
Well,
But yeah, it does.
it, right?
What's that?
Sign extends. No, well,
It is basically sign extending it. So you know that it's a negative number. I think it's what it does.
sure, but how many bits is that? For instance, I see 4 plus 4
10,
plus
I
2.
think.
10 bits. Is that
Which
what you
is
said it to
odd.
be?
No, I set it to 8. I just know Excel does this.
Weird.
Yep.
That's
All right. Offset, this one is also in your spreadsheet, so you can see that I'm just subtracting the decimal index minus the truncated index to find those out. I'm not going to belabor that one. You can do those calculations on your own, paste those in. So we have, oops. Nice. Paste in those formulas. Then we can get our binary value from that offset, and actually can multiply by 2 to the 4 to get that value, which is kind of cool. I love Excel. It makes everything, it works for you.
It's a little better than that.
I don't know, depends. So those are the binary values. If you don't believe me, this is 0.375. This is 0.0625 in a .4 notation, right? The fractional bits. 0.25, that one definitely a no, right? 0.5 is 1000, so you got that. Delta times offset is basically taking that delta value times our offset value in decimal and then showing those values. You can easily do that. Some of those will be negative delta times offsets, right? And you go down and check those values. Offset times delta. You can also use a function to convert that one too. It's kind of handy. Paste this in, paste that function. We're basically going to take this value and convert it to an 8-bit value. And then we can paste those down. Only one of them, we actually get an error on it, which is 42. It kind of breaks the system a little bit. So I had to do a little funky work on that one to get it to work just fine. I had to concatenate it to get it to fit in this one. Using not this value. All right. Shows it with a few extra zeros. All right. Oops, I didn't get it in there, didn't I? That's my value. Base times offset base. So now we're going to add the base value that we had before to our offset times our delta. Calculate those values. I know there's a function to go down to make the formulas go down, but I'm not using that right now. So I get those values, and it's basically our base here, plus that offset value, how far we're going up that linear line to get these values. Then this last one is going to be our truncated value. You can use a truncate function in Excel, that works. Oops. All right, 247. So basically adds base plus offset and delta, and then truncates it down for you manually if you don't like to do the math yourself. But otherwise, you look at this number, 247 would be the truncated value, right? Paste them in. And then basically this is going to be that value there. And as I start adding them, you'll see them add to the graph down below. 247, 242, 185, 105, 33, 1, 22, 87, 231, 250, 217, and 145. Notice the red line, oh, sorry, it's the blue line. Like a red line like Yankee, but the blue line is the actual interpolated waveform, and it looks a lot smoother and cleaner, right? So that's what we're going to be getting out of our system, which is pretty cool, right? All right, and one more thing before we leave today. So that's the final graph, which we already went through. What we're trying to do for the lab is we're hooking it up. So we put a lookup table in VRAM. We initialize a waveform, and then we'll index into that waveform using a 10.16 value to where we can index fractional frequencies and create a function generator that we can essentially use the frequency control knob. That X value is going to be our frequency control knob, that index value into our lookup table. How do you do a lookup table? On your other sheet that I gave you, it has this VRAM initialization. I didn't give you the full VRAM initialization, but ultimately what it's doing is it's creating a VRAM just like we had before, except now we're making it 16 bits wide. So you're gonna have to add 2 bits onto it before you output it to the speakers. On that audio codec wrapper, on every ready signal, you'll output a new value into that index, right? Based on that index value. We'll initialize it with these values, and the way you read them, and I only show you rows 0 through 2, and then 3E and 3F. So there's 64 rows, 1,024 values, but you read them from right to left. And we're going to use 16 bits wide because it fits well into 2 bytes or 4 nibbles. So this is actually memory address 0 on that sheet, and you might want to write that down. Memory address 0 is on the right, and notice that's right in the middle of a sine waveform, right? That's 8,000 hex, which is right in the middle of a 16-bit waveform, right? That'd be like 128 if we use an 8-bit, 1 with a bunch of zeros past it, right? Memory address 1 is right next to it, that byte right next to it. 18 bits would be hard to read. Then address 16 is on the next row, so 0 through 15 on the first row, 16 through 31. I skip a few rows for brevity. You're gonna actually generate these yourself. I'm not giving you the whole thing. And you're gonna actually generate some nonlinear graphs, like a heartbeat or something else, not a, like, you can't do a square wave and you can't do a triangle wave. Those are linear. Non-linear, you're gonna create 2, but we're gonna show you in the next. What?
Saw wave?
No, it's still linear.
It's got non-linear parts.
So I'll show you some tricks to the trade to actually create that for you. You can actually have Excel do it for you, which is awesome. And then our last one, 1,023 is on our last row, and we only have 64 rows, 0 through 63, right? And then we're gonna read, and we're not writing, so those will be set to 0. So that's all I have for today.
Modulated sine wave?
So I actually have that. I'll show you some.
Sine waves.
I used Excel to create some of my own, like a heartbeat wave, and it's actually like a tangent function. Well, if you go back and look at my lecture 25 anyway, you can see how the DDS, I mean, creating a sine wave, this is basically using the sine function and then some lookup value to give you the truncated values between them. So you can extend it to 1024 easily and create one. But then I went through and I created a heartbeat waveform, which is basically a sine function and a cosine function multiplied together, and then index that to, 128 times, and then heartbeat large. That's when I actually went through and created a lookup table to go through more 1024 values essentially. And I had Excel convert it to a hex value, and then I just concatenated all those together to create those lookup tables. You'll do something like this, but a heartbeat waveform kind of looks like this. So I can actually increase the phase to 4, and I get 4 heartbeats. Well, maybe 5. It's more than 1 heartbeat on a sine. Pretty cool. But look at the spreadsheets that I gave you, and it'll help you get there. And we'll learn more about filtering next time. And have a good one.
Filtering.
What's that?
Filtering.
Yep, we're
So-
getting to get into low pass filters and different types of filters. You're
Okay.
actually going to do one VHDL. That's the homework.
All right.
But I'll be, we'll work on that.
So you don't want us to, create a filter that filters out 400 hertz and give you the circuitry in an RLC format, and also give you the transfer function. That's a circuit snooping you have to do.
Oh, wait, sure.
Shear's in the basement. Oh, whenever you do the presentation, I would see the presenter side, which is like the current slide plus the next slide.
You were seeing both of them?
Yeah, I was seeing your side of things, not what was seen on the projector. So I was wondering if you were
Oh.
possibly showing them on the screen.
Yeah, I'm not usually hooked up to there. So
Okay.
that's why.
That's fair.
I didn't realize that. I should have shared the other screen.
Yeah.
I could have shared the other screen.
Because like when you go to this,
See you,
this
Tom.
format, for instance, it seems to have duplicated anyways. You can still see the,
See ya. Thanks.
like, what is it, the spreadsheet and everything. Fine. It's just when you present, that's when it would be different.
Which was on my computer when I do the videos. So you can go back and look at this video, a different video.